Hello everyone, my name is Michał Jastrzębski. I work in Intel, and I was supposed to be here with my good colleague Ale, but due to unforeseen circumstances, he couldn't get here. But without him, this presentation would not happen, so it's his presentation as much as it is mine. And I wanted to talk to you about Kubeflow today. So, Kubeflow. Currently, today, we have a big problem with clouds and machine learning because pretty much we expect to run the trainings on cloud on multiple servers. Right now, data scientists need to really understand what's happening under the hood to be able to do it effectively. And most of them would probably rather do new models rather than learning about networking. And on the other side of the fence, you have DevOps, which are very well suited to reading TCP dump, but they don't really want to mess with all the different models and different scenarios. So currently there is a big disconnect out there, and Kubeflow is a project which is supposed to be helping with that. So Kubeflow is machine learning on Kubernetes pretty much. So we just need to find some place to put a blockchain there, and we have perfect buzzword bingo there. But I personally think that actually those two buzzwords together works really well. And Kubeflow is a project, or pretty much, or a collection of projects which are supposed to make machine learning much easier, much easier to handle for both data scientists. I mean, to make cloud more easier to handle for data scientists and machine learning easier to handle for DevOps. Bridge the gap, which I just mentioned. So this is the Kubeflow mission statement, and we want to run machine learning on Kubernetes, pretty much that. So what it really is right now, it's an umbrella of a collection of projects. And Kubeflow itself, like repository Kubeflow, is a set of KSonnet prototypes to deploy all of that and more things. Besides Jupyter Hub, you also have things like Pachyderm and a lot of great tools for machine learning. And all of those, besides Jupyter Hub, are actually part of Kubeflow umbrella. So things like TensorFlow operator or other framework operators. Katip, which is automatic hyperparameter tuning. So it's a really state-of-the-art technique. And KVC, which is project that it's meant to allow you to handle large quantities of data, like data set, much easier and much more scalable, which is quite critical in this space. But most importantly, it's a community. It's people who are both DevOps and machine learning people together, trying to bridge the gap that and make this thing much better than it is right now. So let's talk about model lifecycle. Model in machine learning terms is this magical entity thing that will turn your question to that will pretty much do the inference, which is execution of the machine learning script. So, for example, when we want to, say, detect cats on a pictures, first we need to train the model, and then we run inference. Or rather, first we need to set up infrastructure for training this thing. Then we need to develop the model, which is iterative. You never get it in the first run, which means you need to try and improve. And then you need to run the training, which kind of works together in parallel with development, and that can take days and hours or days, and heavily depends on the amount of servers and data you have. And at the end, you need to serve the model, which is running this, deploying it on production. When you no longer train it, but it will run inference. And every step of the way, Kubeflow is supposed to be helping with. So today this is gonna be very live demo heavy talk, and this is the infrastructure that I've prepared for it. We have a couple nodes of Kubernetes, and our main storage for data and is GCS. We also use Rook for persistent volumes, and Kubeflow, our latest, greatest first release of 0.1, which is we just tagged it a couple weeks ago. So let's see how each and every step of this, what I described, look in Kubeflow today. And I must warn you, it's pretty early in the game. So first of all, we want to install Kubeflow. And right here, I prepared a Kubernetes environment, which is reasonable. Once internet, come on. Yeah, it's a Wi-Fi thing. Yeah, there we go. We have 17 nodes out here, and we want to deploy Kubeflow on this environment. So so the deployment mechanism is something that we just work on, and our greatest deployment mechanism, which is nowhere near complete, will look like that. Let me just start the script, and I'll explain what happens. There we go. So our main deployment scenario right now is we will use because Kubeflow is very heavily based on KSonnet today. We will want people to be able to use all of the KSonnet's niceties, which means instead of doing like a job, we will want to deploy a toolbox that will then allow you to manage your lifecycle of your Kubeflow application. And it should be done. It is done. So right now I will deploy very basic Kubeflow, but I will suggest you to I suggest everyone to go to Jeremy's talk tomorrow about deep dive. He will talk about much more advanced ways to deploy it. But for a very basic one, we can just do this. And it should run. Yep, it's running. So this is the bare-bone Kubeflow deployed. Took a little bit more than the 5 seconds that was on the keynote, but not that much more. So it's gonna take a couple seconds to spin up. Oh, actually, it's mostly running already. So all of that are main components of Kubeflow. So I wanted to talk about first step of the model lifecycle, and that's model development. With Kubeflow, we, as you can see, we started TF Hub, or rather, it's a Jupyter Hub. And Jupyter Hub, I don't know how much you know about Jupyter, but it's a de facto standard in the industry standard of a web interface for data science. It's extremely powerful. It's formerly known as IPython Notebook, our Jupyter Notebook. And let me quickly show how to spawn your own Jupyter. I mean, Jupyter Hub is spawned, but now we want to start a notebook. So let's start a notebook called KubeCon. It's gonna take a couple of seconds. Oh, it's there. So this is Jupyter. If you're familiar with this, if you pretty much do data scientist, you should be familiar with this interface. And one nice thing about Kubeflow is that when we just make this small hack here, it won't work. but normally it would usually before that it would point us to Jupyter Lab, which is new interface. But hey, Jupyter works, so we can start just create a brand new notebook and start working on our model, on our experiment. All right, come on, work. There we go. So this is how we start working on our model, and one of the first steps would be also understanding data and pre-processing the data. And for that, I encourage everyone to go to Daniel's presentation about Pachyderm, which happens tomorrow, right? Yeah. So Pachyderm is a data pipelines on Kubernetes, and it's also important part in Kubeflow workflow. So once let's say we prepared our data, we created our model, smoke tested it, and it works. Let me show you what the real problem that we're gonna try to solve here. So our problem that we were faced on is detecting brain tumors based on MRI images, and the code that I will try to run is based on UNet, which is developed by Tony and Dina, my colleagues from Intel, based on the paper noted here. It's a quite deep convolutional neural network dedicated for biomedical image processing, image detection. And we will train it on a data set of an MRI images courtesy of University of Pennsylvania. So real life-saving problem here. So our training, once we developed our model in our Jupyter, our training will, let's go to our favorite editor, because at the end of the day we want Python, and just simple Jupyter will not handle the pretty complex code that proper machine learning code looks like, and we can just create a TensorFlow code. We then build images, the Docker image from it, which is the Docker file is quite simple, but we build Docker image and we push it somewhere. And then the magic happens, because once we deployed the Kubeflow, one thing that I didn't show, but it's there, it's an tfjob CRD. That was deployed by TensorFlow operator, which is also part of Kubeflow, and it's the biggest gap bridger right now, because it allows data scientists to not even care about underlying infrastructure. They just say, I want to train my model on 5 nodes with GPUs, and that's what will happen. Let me show you the definition of the tfjob, which is the actual training thing. Okay, test them. Okay. So as you can see, we just pretty much determine how many replicas of the workers we want. We will use namespace kubecon for experiment, and this is our image and all the other stuff. But this part is important, right? This is all the data scientists need to know about the infrastructure, and that will populate the environment variables and configs within the container, and TensorFlow will understand that, which means it will just work, hopefully. So let's try it. Let's run our brain thing. So I made a couple aliases. So so these are our workers that were spawning from this. All of them are training on the dataset that were provided on the PVC. And if we look at first worker, yeah, it's oh, this is, sorry, not this one. It's training, and it will take a couple hours, so I'm not gonna sit here and look at it, just grow, but it will train and converge hopefully at some point. So this is how. After that, once we okay. So first of all, how did this part look without Kubeflow before that? As I said, data scientists needed to know how to run the infrastructure, because they would need to specify exactly which node which worker will land on which node, and what are the networks there, which network they will use, where's data set and stuff like that. It's pretty complicated, especially if you're not in server space. Then right, after all that, after deploying their code and setting up the orchestration manually, they would only then need to be able to reach training. With Kubeflow, you build an image, you specify the TF job manifest, and you're done. So after we trained, training is great for science and stuff like that, but the real usability, the real use case for machine learning is the production inference. It's serving them. And I was hoping I will be able to demo it, but unfortunately it broke. So this is early stage, and I will actually use it as a case in point that I want to make on this presentation, and that we need contributors, and I'll get to that in a moment. But before that, I will show you how it is supposed to be working. So first step, without Kubeflow, serving itself is just a process that you take from that you run from the saved model. However, to run it on production, proper production, you need HA, you need resiliency, which means you need load balancing. You need stuff like AB upgrades, you need rolling upgrades. It's a very much DevOps problem, which we DevOps know very intimately, and machine scientists not really. So this is how it would look like before, and this is how it looks like with Kubeflow. You just you just point to the model, and Kubeflow will deploy it. Will deploy Istio bindings to it, which means it allow you to AB upgrades and stuff like that. It's gonna deploy quite sophisticated infrastructure to serve the model automatically. And the issue is submitted, so hopefully it will be fixed soon. And if you want to learn more about this space of serving the model, I would suggest you visit the demo and presentation of a Seldon project, which will happen this Friday, and which is also, I think it's also going to be based on Kubeflow. So that's serving. And just one more thing. So as I said, we need contributors. I really hope to see you guys join our Slack, join a mailing list. Contribution doesn't need you to be a data scientist or DevOps. There are many ways of contributing, answering questions, publishing issues, publishing documentation. There are lots of ways to contribute, and I would hope that you would join us to this new and quite interesting, fantastically interesting actually, space of machine learning on cloud. Questions? Yeah. Maybe you.
So my question is, do you have a system for versioning the models?
Pachyderm does that, right? Yeah, that's Pachyderm would allow you to do it, and also TF serving itself kind of allows to do it because it's built into it. but not like full-fledged yet. No.
So I assume that when you were training, when you launched that job that was training, there are GPUs there doing that.
That was CPUs. I mean, in this case, it was CPUs. It can be GPUs, but.
But you would have to put it in that manifest that you created that you are using.
GPUs, yes.
Yeah. And is there any, because that's kind of manual and kind of.
It's so depends on how you build, because it's all gonna be based on your labels and scheduling on Kubernetes. So if your DevOps will set up the environment correctly, it's gonna be pretty much as simple as use GPU, yes. Then your code will need to be able to use GPU, because you need different TensorFlow build for GPU and stuff like that. However, that's beside our project. So if your DevOps will set up the drivers and everything in TensorFlow and Kubernetes, sorry, to know where GPUs are and where you just need to specify that you want to run GPUs, and then scheduler itself will handle it for you.
And that's something that would be included in that TensorFlow job specification or something like that?
I believe it is already. Sorry?
So are you distributing the TensorFlow graph among workers?
Yes. This is the. I'm not sure if the code is available anywhere. I will try to make it available in a Kubeflow repository, but I can't promise that it's not my code. But I will try. Sorry.
What about the UIs? I know you have been working a little bit on if you're doing parameter sweeping and you want a lot of instances to run, and you want to follow what happens, then you need to have a shared file system so you can read the output from TensorFlow training.
So I would suggest using like proper log aggregator for that, and there are a couple of solutions like Fluentd and Kibana. And the nice thing about Kubernetes is that we don't need to solve this problem. If you just put your logs on the standard output, the log aggregators will handle those.
My point is that I would like to follow all the experiments through the TensorFlow board, the tensor board. And to do that, I need access to all the files. And I've seen some solutions where
you mean
people are doing what is called NTFS.
You mean the tensor board?
Yes.
So the way to do it right now would be either put it on your S3 or, as you said, shared file system. S3 is probably easiest to handle, and I'm working on we're working on a easier way to kind of handle one to another. But right now it's mostly it's in code. You just need to start a tensor board instance that points to, for example, S3 where you save your logs. But that's all in code. There's not much we can do there, besides mounting the volumes, which we do if you specify those. Sorry. Yeah.
Yeah, I have two questions. The first one regarding, do you have any dependency on the Kubernetes version? Because GPU support in the 1.9 and 1.10 work in different ways.
I don't think so. I mean, quite frankly, I don't run myself GPUs. I run Xeons. So I'm not sure about that. However, because Kubeflow is using Kubernetes primitives, Kubeflow itself probably won't have dependencies, but your particular use case might have, right? Depends on the infrastructure.
Yeah, the second question, is it for single user or do you have any plans to support multiple users? And if you will have multiple users, how to split the resources?
So we just discussed this also yesterday. I think the multi-tenancy and multiple users will be a required feature. That being said, it's not we haven't figured it out yet fully. There is some multi-tenancy within the Jupyter hub itself, but that won't translate to Kubernetes. Right now, my answer would be spawn a cluster for us experiment, but we'll still figure it out. But yeah, the answer It is a required feature for us, as far as I know. So.
Do you have any roadmap for CI/CD of the model? Train, deploy, test.
So there is Katip, which is hyperparameter, which kind of touches that. I personally think CI/CD of the models itself will be very important and very hard. There is Pachyderm, which handles versioning of the data and pre-processing, but the actual models are going to be hard to handle. I would love to see a project like that, quite frankly.
Thank you.
When serving, do you also generate some prediction REST endpoint already?
Sorry?
Do you also generate some REST endpoint, predict REST endpoint?
Well, we do provide, so regular TF serving, but the question was whether or not we, besides actual serving, we provide RESTful endpoints. And serving itself, TF serving at least, uses gRPC by default, but there is, we also have within Kubeflow HTTP proxy that will pretty much create some, I'm not sure if it's proper REST, but it will be HTTP based. So, kind of. Any other questions?
So TensorFlow, PyTorch, and Habit are the three operators you support. Are there any upcoming?
It's an open season, I would say. Like these are three that are being worked on right now. I know that there's some MXNet as well, and not sure if I quite frankly don't know if there is any code published yet, but I know that we talked about it. TensorFlow is by far most mature, and it's not that much mature at this time. But if you want, my answer would be if you want to create, if you have another framework like Tiano, for example, it's very much within Kubeflow scope to handle it, but we just don't have people that wanted that and being contributed to it. Okay, any other questions?
Can you talk a little bit on KVC? Why can't you just use the Kubernetes storage?
So KVC uses Kubernetes storage. So what for Kubernetes? So KVC right now is a kind of caching mechanism. So the main use case of KVC is pretty early. So the use cases are still TBD. But the one that we are using it today is that when you have your huge data set as free, like object store somewhere, and accessing those data is actually quite a bottleneck. It's there's the overhead of networking that when you want to, for example, ping for every image in the training set, which can be hundreds of thousands of images, it makes the training much longer. So what KVC does, it pulls these images and saves it on a local volume, which then you mount to a TF job. So it uses the storage, but it kind of abstracts the storage backend and allows it to be more local to the training job. It's a caching problem. But as I said, the use cases are still being determined, and I know about a couple different ideas, like again, Pachyderm being caching their pre-processing. So, for example, data flow is data pipeline itself is quite a big thing, because when you, for example, go have the image, you want to resize it and recolor it and do the pre-processing of the data, and you want to save those images, that's also going to be Pachyderm/KVC problem. So yeah, we are using the storage, but we just do more with it.
Do you know of any cases of people using Jupyter Hub with GPUs? And if so, like, how are you managing those resources without just talking?
Yeah, let me show it to you. Actually, it's okay. I will need to restart the.
One problem we have is we want to attach Jupyter notebooks to GPUs, but people will just do some stuff and leave them running.
Yeah, I mean that's gonna be a problem. But so when you see start my server, you can, for example, put the nodes for the scheduler that will schedule it on GPU nodes. But the problem that won't solve it. The problem that you mentioned, it's like you need to prune your maybe run some cron job that will kill the running kernels, stuff like that. But
Do you ever have to worry about like deciding which ones are actually being used and which ones are not?
so disclaimer: I'm not running the data science. I don't have data science group. So, I don't see how I could do it really.
Yeah, it's tough.
It is, yes. Any other questions? All right, I guess. Thank you for everyone for coming, and hope to see you on the Slack and in our community.